Shri Gurubhyo Namaha, children. Today I am going to continue with the same Wheatstone's network since I was not able to complete it in the last class. Now let me again start with the introduction part of Wheatstone's network, children. So once again I am going to teach you what is a Wheatstone network about. Okay. Now this Wheatstone network is an application of Kirchhoff's law. Now this is used to compare resistances. Now there are a series of resistors that are connected to this network. Now we can compare the value of the resistances and also we can determine the value of an unknown resistance. Now out of this 4 resistors which is there in the diagram, any one resistance can be an unknown resistance. So with the help of the known 3 value of resistance, we can determine the value of the unknown resistance. So this is how the Wheatstone's network go. Now let us see how the circuit is made up of. Now look at this diagram, children. It consists of 4 resistors. Now P, Q, R, S. Now this forms a bridge network. This appears like a kite-like thing. Okay. So they are arranged in such a way to form a network, and you have a galvanometer that is connected between B and D. Okay, now this also has a resistance. We are going to calculate the resistance of galvanometer or also here when we apply Kirchhoff's rules here. So galvanometer, now it is connected between B and D junction. Okay, and you have a battery connected between points A and C. So this is a battery whose EMF is given as psi. A battery is connected along AC, points A and C, and a galvanometer along B and D. Okay, so this is how the circuit goes. Now I am going to apply Kirchhoff's current rule to the junction B. So applying Kirchhoff's current rule in junction B. So let me apply Kirchhoff's current rule in junction B. Look at this junction B. Now the current entering the junction is I1. So it is plus I1. The current leaving the junction is Ig and I3. So it is plus minus Ig and plus minus I3, which is equal to 0. So I take this equation to the other side. Okay, let me write like this. We'll do it later on. Okay, now next we are going to apply again Kirchhoff's current rule. Where I am going to apply now is in junction D. So when I apply Kirchhoff's current rule to junction D, again the current entering here is plus I2. Now as far as this Ig current is concerned, it is also entering. So it is plus Ig. Now here the current is leaving. So plus minus I4 equal to 0. So this is my equation 1. This is my equation 2. Okay, so in both the junctions I have applied current law. Now I am going to apply, let me go to the next page, voltage law. So first next applying voltage law to the loop. So whenever we talk about voltage law, we need to talk about as a closed loop. So the closed loop which I am going to take now is ABDA. Look at the diagram. Go back to the diagram. Where is ABDA? Look at the diagram. So it is ABDA. Once again, it is a closed loop. See here, AB, BD and DA. So this is a closed loop that I am taking. Now I am going to write Kirchhoff's apply voltage law and write the equation. Okay, so let us start with this lead. Now here the direction of current and my direction are the same. So it is P into I1 or I1 into P, product of resistance into current. Okay, So this is plus I1P. Then again, when comes to this loop, this is galvanometer current, which is Ig, and galvanometer resistance, let us take it as G itself. So product of resistance into current will be plus Ig into G. Then when come to this lead, you have the value of the resistor to be having resistance R, and the current here is in this direction. Actually, from here to here, then from here to here, the direction should be from D to A. But look at this direction, it is from A to D. So when I write the product of current and resistance here with the negative sign, I will write, okay, that is equal to 0 because there is no cell here. So algebraic sum of the EMF will be 0. So let me write the equation here. So I will write I1P plus Ig into G minus, what is the combination here? I2 into R. So okay, so it is I2 into R equal to 0. Now this is my equation 3. Right? Now once again I apply. Now this time applying voltage law to the loop. Now this time I'm going to apply A, B, C, D, A, full loop. A, B, C, D, A. Once again, A, B, B to C, C to D, and D to A. So for this full loop, I'm going to apply. Okay. So let us see the direction of current from A to B. From A to B, it is I1. Okay, plus sign can be used. From B to C, product of current into resistance, plus sign. But here, it should be from C to D, but it is not from C to D, it is from D to C. So here, when I write the product of current and resistance, I should have a negative sign. Then from D to A also, I should have a negative sign because look at the direction of current. My direction is like this. Now current direction is like this, but whereas here it is like this. So it is opposite in these two leads. So I have to write the product of current and resistance with a negative sign when I write to these loops. So let me write that. So current applying voltage law to the loop. What is the loop here? A, B, C, D, A. Okay ma? So I will write I1P plus I3Q. Look at the value of the current here. It is I3Q. Next, minus I4S. So, minus, refer your diagram children. Minus I4S minus I2R equal to 0. So, this is my equation 4. Okay. Now, go back to the diagram. Right. Now, I'm going to explain you a very important thing, children. Look at the circuit diagram once again. Now, when a current is given, when a battery is connected and you send current from point A, that is from junction A, the current is getting splitted up. Now, let us assume the current here is getting splitted up in these two leads. So when in this lead, if the current is increasing, right, at this point, the current is 0 as far as this lead is concerned. So it is going on increasing, 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 increasing. At a point B, there is a value of potential. Yes, the potential here, the voltage is given. So here it is increasing, and here also it is going on increasing, increasing at a point D and B. Now here the potentials are the same. So when the potential is going to be same, okay, at that point the galvanometer shows 0 deflection. From here the potential starts varying. It starts increasing. It's keep on varying along this lead and along this lead. And now at a point B and D, both the potentials will have the same value, and at that point the galvanometer shows 0 deflection, which is considered to be the balance point or bridge point of the network. Okay, so in that case, all the resistance will have the same value. So in that case, what will be the value of Ig? So let me write here, when the points B and D are at the same potential, the value of Ig is said to be 0 and the bridge is said to be balanced, and the bridge is said to be balanced. Okay, ma? Is it clear? So, in that case, when Ig is going to be 0, look at the first equation. In this first equation, Ig will be equal to 0. Second equation also, Ig will be equal to 0. In that case, I have the value of I1 is equal to I3. Similarly, I2 is equal to I4. Okay, let me name this as equation 5. Let me name this as equation 6. Now look at this equation. Now here also I have the value of Ig. Now this also turned out to be 0. So in that case I have I1P is equal to I2R. This is my 7th equation. Is it clear? Now I take this term to the right hand side. Now here also this I3 when comes to the right hand side it becomes plus I3, I4 when comes to the right hand side it becomes plus I4. So here are the equations when I consider Ig to be equal to 0. Okay, now substitute these values, that is I1 equal to I3, I2 equal to I4 in this equation 4. So when I substitute, now I am going to substitute, children. Okay, now I1P, let it be like that itself. So I1P plus, now I3Q is there, right? So instead of I3, I will substitute I1 itself. So I1Q minus, I know the value of I4 to be equal to I2. So substitute instead of I4 as I2S minus I2R equal to 0. Now take this minus sign to the right side. So I1P plus I1Q equal to I2S plus I2R. Now take I1 to be common here. I have P plus Q inside, and here I2 take it as common. I have R plus S. Now this is my equation 8. Now I am going to divide 8 by 7. Okay, so divide the equation 8 by 7. Okay, so I have I1 P plus Q by I1 P, okay, equal to I2 R plus S by I2 R. So I2, I1 gets cancelled. So it is P plus Q by P is equal to R plus S by R. So P by P, I can write this as P by P plus Q by P is equal to R by R by plus S by R. So here also it gets cancelled. It becomes 1 also gets cancelled. So here is the equation. Q by P is equal to S by R, or P by Q is equal to R by S, which is the balance condition. Okay, so this is the bridge balance condition. Okay, now under this condition only, that is P by Q equal to R by S, in the sense the ratio of these two resistors is equal to the ratio of these two resistors. So in this condition where the potential is going to be the same along this junction, the galvanometer will show zero deflection. Okay, so in this condition, when we know the value of the three resistors, now we can have one resistant to be the in whose value is to be determined to be connected here. Now we know the values of all the other three. With that we can determine the value of the unknown resistance. So this is the use of a Wheatstone network. Okay, hope now we are clear with the concept. Now with this concept in mind, I wanted to discuss the sum which is there in your textbook, page number 1111, example 2.24. What is the value of X when the Wheatstone network is balanced? So there are four resistors in the third lead where R is equal to X plus 400. You need to find out the value of X there. Okay, so let me solve. P by Q. P by Q equal to R by S. So what is P? P is 500, Q is 800, R is X plus 400 and S is 1000. Okay ma? Now you have to have the value of X here. So bring that term alone to the left side. So X plus 400 equal to, I have 500 by 800 into 1000. So simplify to get the answer. So it will be X plus 400 equal to 625. When I simplify this, I will get 625. So X is equal to 625 minus 400, which is 225 ohm. So this is how you will find out the value of X. Okay, clear? Now we are going to discuss one more sum from your textbook, children. Book back exercise. This one. The rod given in the figure is made up of two. Now this is this is not based on Wheatstone network, but I have left a problem when I was teaching resistivity for you. So I wanted to complete this, so I am doing this now, right? So the rod given in the figure is made up of two different materials. Both have square cross sections of 3 millimeter side. The resistivity of the first material is 4 into 10 power minus 3 ohm meter and it is 25 centimeter long, while second material has resistivity of 5 into 10 power minus 3 ohm meter and is of 70 centimeter long. What is the resistance of rod between its ends? Now in your textbook it is given as resistivity. It is not resistivity, children, it is resistance. Okay, so let me solve this. Now both are different materials. So the resistivity of the first material is given as rho 1, which is equal to 4 into 10 power minus 3 ohm meter, children, and the length L1 is given as 25 centimeter, which is 25 into 10 power minus 2 meter. And area, of course, you know, area for the both the material is going to be same, so meter square. So area is given as 3 millimeter. So square of it is 9 into 10. 3 millimeter is 3 into 10 power minus 3 meter. So square of it will be 9 into 10 power minus 6. Okay, meter square. Is it clear? Right. Now, and the second value, resistivity, is given rho 2. Rho 2 is 5 into 10 power minus 3 ohm meter, and L2 is given as 70 centimeter, which is 10 power minus 2 meter. Now we need to find out what is the resistance between its ends. So first we need to find out the value of resistance R1, then find out the value of resistance R2, then the average of it. R equal to R1 plus R2 will give the value of resistance between the two rods. So let us move about it. So first find out R1. So R1 will be rho 1 L1 by A1. Am I right? So rho 1 is 4 into 10 power minus 3. L1 is 25 into 10 power minus 2 divided by 9 into 10 power minus 6. Okay. So 25 into 4 is 100 into 10 power minus 3 into 10 power minus 2 divided by 9 into 10 power minus 6. This is also 10 power 2. So 10 power 2 minus 2 gets cancelled. So 10 power minus 3. Now when this goes up, okay, this becomes plus 6. So minus 3 plus 6 will be 10 power 3, which is 1000. So 1000 divided by 9. This is R1. Okay, similarly R2 formula, rho 2 L2 by A2. Rho 2, what is the value of rho 2? It is 5 into 10 power minus 3 into 70 or 75? 70, okay. 70 into 10 power minus 2 divided by 9 into 10 power minus 6. So again, when I simplify this, I will have the value 7 5s are 35, right? So 350 into 10 power minus 5 divided by 9 into 10 power minus 6, children. Okay, so when you take this 6 to the numerator, becomes 10 power 6. So 10 will be there. So 350 into 10 will be 3500 divided by 9, which is the value of R2. So the resistance of the rod between the ends is taken as R, which is equal to R1 plus R2. Substitute the value of R1 to be 1000 by 9 plus the value of R2 is 3500 divided by 9. So the total resistance will be 4500 divided by 9, which is equal to 500. So the value of R is 500 ohm. Okay, ma? Is it clear? So this is how I have solved the problem. Now in your textbook, I think I have discussed, take page number 123, children. First problem I discussed. Second problem I didn't discuss. I have discussed that. Third also I discussed a problem. I told you to do this problem. Fourth one also, it is based on the temperature coefficient of resistance, direct formula. The resistance of a nichrome wire at 0 degree Celsius is 10 ohm. If its temperature coefficient of resistance is 0.004 per degree Celsius, find its resistance at boiling point of water. Boiling point of water is 100 degrees Celsius. So you need to find out R100. Okay, and comment on the result. You know that when temperature is increased, resistance also will increase. Now temperature at 0 degrees Celsius, the resistance is 10 ohm. If the temperature is going to be 100 degrees Celsius, definitely the resistance will be greater than 10 ohm. So you have to find that. Now alpha is given, temperature coefficient of resistance is given. So you need to find out the value of resistance at 100 degrees Celsius. So formula RT equal to R naught into 1 plus alpha T. Write the formula, substitute the value, you will get this answer. Resistance you will have 14 ohm. Try it, it is a very simple problem. Okay. Then fifth sum I discussed, children. Just now I discussed fifth sum, and the remaining sums, depending upon the concept, I will finish off. 10 and 11 also I completed. 10 and 11, and try this sum, children. Question number 13. Two cells each of 5 volt are connected in series across a 8 ohm resistor and 3 parallel resistors of 4 ohm, 6 ohm and 12 ohm. Draw the circuit diagram for the above. I think I discussed this sum. Just check this, okay? So I think I have done this. If I have not done this, please try it at home. You can solve this sum easily. I think I did that. Anyhow, just go through it and let me know. Okay. So keep on revising these problems. We'll be continuing with the next topic tomorrow, children. Okay, ma? See you.